Welcome to Solar Radiation Fundamentals for Solar Photovoltaic Systems. Part 3, we cover the locating the sun's position using a solar path diagram, defining the solar window, and plus we access some solar radiation data resources and quantify the effects of collector orientation on the amount of solar energy received. The sun's position in the sky at any moment is relative to an observer is defined by two angles. The solar altitude angle is the angle between the sun's rays and the horizon, the altitude angle. The solar azimuth angle is the angle between the horizontal projection of the sun rays and geographic due south. The azimuth angle. The zenith angle is the angle between the line to the sun and directly overhead. The zenith angle. The zenith angle and the altitude angle are complementary angles. The addition of the two angles always equals 90 degrees. At the equinoxes, at every point on Earth, the sun rises and sets due east and west respectively, and days and nights are exactly 12 hours. On the equator, the sun traverses the east-west plane and reaches zenith twice per year at the equinoxes. In the northern hemisphere at the summer solstices, the sun rises and sets north of east and west, respectively. Days are longer than nights at high altitudes. The sun remains in northern sky all day at latitudes lower than the Tropic of Cancer, and the sun reaches the highest altitude of the year at latitudes higher than the Tropic of Cancer. In the northern hemisphere at the winter solstice, the sun rises and sets in south of east and west respectively. Nights are increasingly longer than days at high altitudes, and the sun remains in the southern sky all day. The sun reaches the lowest altitude of the year at latitudes higher than the Tropic of Cancer. The sun movements are best shown in the following charts called sun path diagrams. Here are the sun paths for the equator, 0 degrees at the equinoxes, summer and winter solstices. Envision this chart of sun positions as a 3D cylinder. The left axis 180 degrees east connected to the right axis 180 degrees west. For these charts, the reference for due south is an azimuth angle of 0 degrees. The azimuth angle along this axis is 0 degrees. The altitude angle along this axis from 0 to 90 degrees. On the winter solstice, which occurs on the 22nd of December, this blue line represents the path of the sun. On the equinoxes, the vernal equinoxes, this green line represents the path of the sun. On the summer solstice, the path of the sun is represented by this red line, here and here. For example, where will the sun be at noon on the winter solstice? What will be the azimuth angle and what will be its altitude angle? The winter solstice blue line is shown here. There is the time noon shown, 8 a.m., 10 a.m., 9 a.m., 10 a.m., 11 a.m. and noon. The azimuth angle, as you can see, is 0 degrees, and the altitude angle is shown as approximately 70 degrees. To review, the left axis or y-axis shows the sun's altitude at different times of the day. The bottom axis or x-axis shows the sun's azimuth angle from degrees. For example, again, on the equinox at 12 noon, where will the sun be? The equinox occurs on the green lines. So locate the green equinox line, find the time of 12 noon. On the line and check the altitude angle. The altitude angle is 90 degrees and the azimuth angle is 0 degrees. Now we have moved the sun diagram to 15 degrees north. For the same example, the sun's altitude angle on the equinox at noon is now 75 degrees. Now we move to 30 degrees. For the same example, the sun's altitude angle on the equinox at noon is now 60 degrees. When the sun's what is the sun position at 8 a.m. on the winter solstice for this position? Locate the blue winter line, the winter solstice. Find 8 a.m. There's 8 a.m. on the line and check the altitude angle. The altitude angle is approximately 13 degrees and the azimuth angle is approximately 50 degrees. At 45 degrees north, for the same winter solstice at 8 a.m., the sun is at an altitude of 3 degrees and the azimuth angle is approximately 55 degrees. At 60 degrees north on the winter solstice, the sun does not rise above the horizon until 9:30. As seen by the blue line, there is 10 a.m. and below is 9:30. At 75 degrees north on the winter solstice, the sun does not rise at all. The blue line is not visible. The sun remains below the horizon. The solar window. The solar window represents the range of sun's paths for a given latitude between winter and summer solstices. As latitude increases from the equator, the solar window is inclined at a closer angle with the southern hemisphere horizon. Sun paths and days are longer during summer, shorter during winter. For any location, the maximum altitude of the sun at solar noon varies 47 degrees between the winter and summer solstices. PV arrays should be orientated towards the unobstructed solar window for maximum solar collection. This is the key point. PV arrays should be orientated towards the unobstructed solar window for maximum solar energy collection. The orientation of PV arrays and other solar collectors is defined by two angles with respect to the collector surface. The collector azimuth angle represents the angle between due south and direction the collector faces. The collector tilt angle represents the angle the array surface makes with the horizontal plane. The solar incidence angle represents the angle between the sun's rays and the normal perpendicular angle to a collector surface. The orientation of PV arrays and other solar collectors is defined by two angles. The collector azimuth angle, shown here, is the angle between due south and the direction the collector faces. The collector tilt angle is the angle that the collector surface makes with the horizontal plane. Maximum annual solar energy is received on a fixed surface that faces due south and is tilted from the horizontal at an angle slightly less than the local latitude. Fall and winter performance is enhanced by tilting collectors at an angle greater than latitude, and spring and summertime performance is enhanced by tilting collectors at angles slightly lower than latitude. For the central and southern US, latitude tilt surfaces with azimuth orientations of plus or minus 45 degrees from due south and with tilt angles plus or minus 15 degrees of local latitude will receive 95% or more of the annual solar energy for optimally tilted south-facing surfaces. This is the good news about solar energy, is there is a very wide angle that you can point your solar panels to and still receive at least 90 to 95% of the annual solar energy. Optimal energy performance of PV arrays is achieved by facing the arrays due south in the northern hemisphere, surfaces with azimuth orientations of plus or minus 45 degrees, shown in this diagram here, will receive still 95% of the solar energy. Here we can see the effects of the collector tilt and azimuth on annual solar energy received. For example, here this is showing the available irradiation for a collector facing due south at approximately 15 degrees, and we can see if you are facing from an azimuth angle of 180 to 240 or from 180 to 135, you will still receive 190 to 95% of the total solar energy. As you move north, the amount of energy is reduced and moves higher up in altitude. In the USA, data is available from the National Renewable Energy Lab, but there are various world locations including Canada which are shown in PV Watts 1 or Red Screen. Red Screen is available as a download from the Canadian Natural Resources website and is a great tool to complete projects for solar energy or any renewable energy project. That is also available from the Department of Natural Resources in Canada. PV Watts is used to evaluate solar energy collected and the performance of grid-type PV systems for any array azimuth and tilt angle. Users select the country and city from the map and enter the size of the PV system, array orientation, and any derating factors which will be studied later. Results give monthly and annual solar energy received and PV system AC energy production. Use PV Watts 1 for locations outside of the US. Use PV Watts 2 for locations within the US. Here is an example of a PV Watts output showing your location here as Daytona Beach, the state, the latitude, elevation, the DC rating for this PV system. It's going to be a 500 kilowatt system, a derating factor of 0.75, an AC rating factor of 375, which is 500 times 0.75, which is the derate factor. This is a fixed tilt system with an array tilt of 29 degrees, an array azimuth of 180, which means that it points due south. The results show by month 1 to 12 the solar radiation per day, the AC generated for this system, and the energy value based on a specified cost of specified by the user. Finally, sun tracking arrays improve the capability of the system to collect solar energy. You can either have a 2 tracking axis system which can rotate the collector either way and collect maximum amount of solar energy. You can have a system that collects only one way, which will be optimal for seasonal adjustments, or another one which does east-west tracking. In summary, the solar radiation received on Earth is affected by the Earth's movements and the atmospheric conditions. Solar irradiance power is expressed in units of watts per meter squared or kilowatts per meter squared and is measured with a pyranometer. Typical peak values are around 1000 watts per meter squared at sea level facing the sun around solar noon, used as the rating condition for PV modules and arrays. Solar irradiation, which is solar power integrated over time, is expressed as units of kilowatt hours per meter squared per day. Solar energy resources data are used in sizing and estimating the performance of PV systems in various locations with collector's orientation. The solar window defines the range of sun paths between the winter and summer solstice for a specific location. PV arrays are oriented towards the solar window for maximum energy gain. Complete the exercises for this section, the PV watts exercise and the multiple choice quiz. Thank you for watching, and if you have any comments or questions, contact us at contact@sunacademy.com. Thank you.